Today, as I said before, I will talk about temperature measurement techniques. As you already know that heat flow is a derivative measures, and we need thermal conductivity and the geothermal gradient to measure it. And in the first session of this day, Graham talk about the thermal conductivity measurements, and today I will continue with the temperature measurements. But generally, my presentation focus on the continental temperature measurements, because after me, the next presenter is going to talk about the marine heat flow measurements and explanation about the temperature measurements in the marine environment is going to be given there. And let's start. As I said before, temperature is the most important parameter that we need to use calculate the reliable heat flow studies on the Earth. And as we know this again, temperature increases with depth in the Earth. The increase is partly because of the heat is coming out of the hot interior of the Earth, and also it is being produced, the heat energy is being produced with the rocks by the radioactive heating. And for the valid and reliable heat flow density values at the surface, the equilibrium temperature gradient must be obtained. So how we can measure temperature at the Earth? There are some direct measurement techniques and indirect measurement techniques, but today I just focus on the direct measurement techniques, and maybe indirect temperature measure would be the another topic of the another speech. So for the direct temperature measurements, we need unlike the gravity or magnetic data, we need to send our tools inside of the Earth. So we need tunnels, we need boreholes, we need wells to measure the temperature of the Earth. So we can use continuous temperature logs, bottom hole temperature, distributed temperature sensing, and temperatures from drilled steel temps. And for the marine heat flow data, we use the heat flow probes. I just quickly talk about indirect methods also. As you know that direct temperature measurements are somehow limited where we have boreholes on the Earth. So if it's not possible to get a direct heat flow measurements, we can make some estimations, but they are not the real measurements, and sometimes the uncertainty calculation of determination of the uncertainty can be a little bit tough. We need to take into account this, but heat flow also can be estimated using the groundwater chemistry methods, crude depth points, sonolith data, electrical resistivity data, seismic cutoff depths, and the bottom simulated reflector methods. For the direct heat flow measurements, for the direct temperature measurements, there are several available instruments, and we can put them in a four groups. The first one can be the wireline tools and the probe sensing tools, which needs to be constant electrical contact with the surface. And second one can be the self-contained thermometers. This kind of thermometers use generally bottom hole temperature measurements. And the third one, autonomous computer tools integrated with the memory units for the recording at time-dependent temperature logs. And the last one, distributed optical temperature sensing system, enables simulations recording over a full interval. I will give explanation of each of them. The first one is the continuous temperature logs, which is the temperature that we really rely on. And high temperature, high pressure, high High precious temperature logs are generally most reliable data in the heat flow studies. So, because the tools used to have the typical sensors, they respond to us in order the few seconds, and which really provides a good advantages. And also, using the continuous temperature logs, we have multiple temperature measurements at the several depths. This is what we need. That's why we would like to, as much as possible, we would like to record temperature, and we would like to calculate geothermal gradients from the continuous high quality temperature logs. But we need to be careful while recording and after calculating heat flow or the geothermal gradient volumes from the temperature logs. We need to take into account that we need to be careful about all the measurements should be taken under the equilibrium conditions. For example, while during our measurements, when we send the our tools inside of the borehole, it can disturb it can change the equilibrium condition of the borehole. So it is better to use we record the temperature while we are passing through the borehole, while they are descending to do the bottom of the borehole. And if we do the reverse, if we do the opposite, our temperature measurements can be recorded under disturbed conditions. So, and in addition, relatively low speed and stop and go techniques help us to keep the borehole close to the equilibrium condition. And if the measurements are taken above the water table, the temperature sensors needs more time than they need in recording in the below the water table, because it takes time to reach the equilibrium condition between the tool and during the measurements, temperature measurements, we don't directly measure the temperature of the logs. We measure the temperature of the water inside of the borehole. That's why it will, if it is filled with the water, and if we start the temperature measurements under the water table, it will give us more reliable data. Other technique is to distribute temperature sensing, and it utilizes the Raman effect, where the light is scattered along any optical fiber, allowing the temperature to be determined across the entire fiber length by analyzing intensity of the backscattered light over the time. These DST temperatures provides us very we can use these devices with these techniques to get temperature measurements until sometimes it up to 550 Celsius degrees, and theoretically there are some kind of papers. Theoretically, it can be proved that they can measure the temperature until 700 Celsius degrees. This is very useful for us, but unfortunately, their precision is very low. That's why it's only used, or it is also possible to leave these tools inside of the borehole. So we can, if we want to monitor a transient event, or we would like to monitor temperature difference for the long term, we can use this method. So bottom hole temperatures and the real steam test, these are the temperatures. Let's start with the bottom hole temperatures. Bottom hole temperatures are the single observations. Generally, record took very short time after the drilling. So after the drilling, we expect that our boreholes are not, they don't reach the equilibrium conditions. So they need to be corrected. And of course, bottom hole temperature, if we have more than two temperature measurements under the Earth, inside of the Earth, we can calculate geothermal gradient, but it is highly recommended that bottom hole temperature should be corrected. And it is not the same for the dream test. Temperature estimations or temperature calculations from drill steam test, because it is generally we know that drill steam test reflects the show us the approximately real formation temperature. So we can trust this drill steam test measurements. But unfortunately, it is this classical standard procedure, even if it's the classical standard procedure in the hydrocarbon explorations also, it's not much that used in the other type of explorations. So, and it can be used generally without any correction, but if the fluid flow inside of the borehole is very slow, and there can be sometimes, some kind of gas components depending on the resource area. In this kind of situation, we need to be aware of them, and we need to report it, and we need to, if we can correct these effects on this DST measurements. So, as I said before, it's highly recommended that correction of the borehole bottom hole temperatures, because several studies shows that generally uncorrected bottom hole temperatures are generally lower estimates the lower values than the true temperature of the formation. So, and we need to correct the bottom hole temperatures, and the amount of the correction depends on the increasing depth, and at the same time, this increase cannot be linear, and the correction even maybe decrease with the grid depths. So there are some different kind of models has been developed or suggested for the several authors, and each of them are useful for the certain kind of situations. I need to say here that using a single bottom hole temperatures can be misleading sometimes. I will show you an explanation and example a few minutes later. That would we highly recommend that if we, even for the correction, we need more than 1 pHT temperature. If, for example, if we have multiple pHT values recorded in the same boreholes, but at different times, that will really help us. I also would like to mention some most commonly methods used for the BHT corrections, and as I said before, maybe maybe more than 20 equation you can see in the literature, more than 20 to 25. There are several types of corrections, but I would like to concentrate on their general idea and what is the general mathematical models behind them. I would like to concentrate on them, and if you can, maybe in the futures we can make another session and we can make another lesson to describe their applications to the certain temperatures. But now today I will give a general explanation about the corrections. The first one is the AAPG correction. It is the most used, how can I say, in the worst case we can use this correction because it's also known as the empirical correction, and if we only know the depths, we can apply this correction, so somehow we can correct our BHT values. Yeah, it is not perfect, but better than uncorrected bottom hole temperatures. And Horner plot correction, probably most of you already heard it before. Most commonly used method for the bottom hole temperature correction, and there are some kind of limitation in this method. As you can see in the equation, given equation, these parameters, after, how can I say, these parameters in under the limit condition, if these parameters limits to the infinity, this correction this correction would not work for us. And in this kind of situation, some researcher suggested naive version of this, the Horner correction, Horner plot correction. And the first one is the line source exploration method. It is developed by the Ballard, and sometimes it is, when if we have problems application, if we have some limitations by application of the Horner method, we can use this one. But when we want to apply this, we need to use the thermal divisivity of the medium. And as I said before, every kind of application correction method has some advantages and disadvantages. And after this, cylindrical source methods also developed by the researchers, and this is also similar to the Horner method, coming from the base, how can I say, base mathematical model. But in this method, it is assumed that a medium with homogeneous thermal properties, and however, instead of the line source expansion, they suggested that the cylindrical source to correct their bottom hole temperatures. As I said before, there are some kind of limitation also for this correction. It highly depends on what you have. If you have shut-in time, if you have, if you know the if you know the detailed information about your ball, and you can apply maybe any of them, and maybe two of them, and you can compare the results. But every kind of calculations or correction have its own limitation or advantages. So what else can be, what can cause an error for our temperature gradient measurements? When you go to the field and when you set up your tools and you start the recording your temperature, what kind of the effects can be an error on your measurements? These are the estimation of depth. It is the most important one, according to me. Yeah, not according. It's one of the problematic issues while you are thinking that you're recording maybe 10 meters or 50 meters, there can be some kind of differences shifting in your recordings. You need to be aware of this. All the measurements should be, we would like to, of course, maybe it cannot be possible every time, but we would like to get the temperature measurements under the in the case boreholes, which prevents some convection effects, or maybe some kind of intra-borehole effects. We always prefer to use the cased borehole temperature measurements. And as I said, the convection within the borehole can cause an error. Inclination, if there is an inclination inside the borehole, this also can be an error. And the temperature perturbation due to the drilling, this is the, of course, most important one, can cause an error on the temperature measurements. You can see you can see here how the drilling affects the temperature measurements. I get this information or example from Andrea Forster paper. Um, you can see at the left side there are multiple temperature logs, and the first one, between the first one and the last one, there are 7 years. And as you can see, after the 7 years, the solid line reflected the the straight line reflects the equilibrium temperature. And before temperature records, before this date, it's somehow corrected in the disturbed conditions, and which means that, yeah, and you can see that we call this point as a crossover point. There are four temperature logs here, and the first one, the bold solid line, is this one, and the second one is B, the third one is the C. You can see that above this crossover point, while the temperature tends to increase in the upper part of the borehole, below this crossover point, they reflect the opposite behavior. They show the opposite behavior. And this crossover point generally depends on the depth of the borehole, and also it depends on the shutting time. And as you can see, there are some kind of equilibrium BHT temperature here. Even the equilibrium BHT temperature means that they are corrected one, but unfortunately, only maybe one, or how can I say, maybe one of them or two of them reflects the same true formation temperatures, like the log reflects. And at the right side, you can see that two different temperature measurements, continuous temperature measurements. The first one is just only recorded after 48 hours after the drilling, and the blue one. And you can see that, and we can also put a crossover point here, and before the above of this crossover point, you can see the temperature are higher than what it should be, and below of this temperature also, this crossover point are lower than the true temperature measurements. Although we can also see that BHT, uncorrected BHT with the blue dots, they are uncorrected one. Even they corrected for somehow applied different kind of in this study, they applied two different corrections for the BHT, and we can still see that even corrected BHTs are not so close to true temperature, true formation temperature. Also, here we can see the intra-borehole effects. Sometimes, as I said before, sometimes casing, we can record our temperature measurements under the uncased boreholes in this kind of situation, or if there is pressure differences between the lithologies, and they can be, there can somehow a fluid movements, and we can see them at the at the left side, we can see them as a upflow. This upflow does not mean that temperature. This is just a borehole. If we, if I had a bottom hole temperature, and if I record this bottom hole temperature, and I would probably get a I will calculate a wrong thermal gradient from a single bottom hole temperature. But from here, I can recognize that there is an upflow in this temperature gradient, temperature measurements, and the opposite things occur here. Probably the differences between the pressure or the head of the inside of the boreholes can somehow small convections, or how can it's the convection movements inside of the borehole, and I can see them as a dome, flow dome. And it is also possible to see if there is a lateral flow. Generally, we can see this kind of effects at the upper part of the bottom temperature measurements. These effects should be eliminated, and we need to take into account. We need to decide that, for example, you can see that in this on tree, the temperature measurements, temperature logs. So I can say the temperature logs. The black one are the temperatures, and the blue one the geothermal gradients that I calculated. This is from my site. This is from Turkey, and this is from this some data from my PhD thesis. You can see that if I don't interpret, if I don't see if I can't see or if I can't read my temperature precisely, maybe I can make a wrong thermal gradient calculations for the same borehole. So we need to be, careful by explaining or calculating geothermal gradients in the boreholes. So when we want to, if you want to calculate geothermal gradients, it is coming from the, geothermal gradients. We said, what is the temperature differences between the certain depths? And I took them from the Sven Fuchs slides. It is very informative. It gives very informative explanation how we can calculate the geothermal gradient. Let's look at here. If we have the surface temperature, if we have a surface temperature at depth of the 0, and the temperature at the end of the borehole as a 138, geothermal gradient should be the T2 exit T2 minus T1, Z2 minus Z1, and differences between the temperature should be divided by the temperature differences between the depths. So we can calculate geothermal gradient as that. But let's look at here. If I had just the bottom hole temperature, and if I recorded this bottom hole temperature approximately at the 2060 meters, 2,600 meters. This can give me an error. If I only have one, if I had only one temperature recordings, this can mislead me while calculating heat flow temperature, and probably I would calculate a higher temperature gradients depending on because as far as I understand from here, there is a increase in the temperature here, and this can mislead me, and I need to be careful, and that's why we shouldn't use only single bottom hole temperatures to calculate geothermal gradients while calculating geothermal gradients. And yes, and this is my last slide. I put a diagram from the Breathmore and the Coos and the cool books, and they give us an explanation which method should we follow if we have multiple, if we have want to calculate the geothermal gradients. First, if we have a boreholes and that on the area that we are interested in, and if the holes are accessible, and we need to get a high precision, high quality temperature logs. And if we don't have any borehole available, and we can concentrate on are there any other geophysical logs on this area, and from them we can calculate it, maybe groundwater. We can get the geothermometer, we can apply their geothermometers, and we can calculated the temperature there, and maybe we can reach out to the DHT and BHT temperatures there, and we can also, if it is possible, maybe we can get the indirect, we can apply for the indirect methods, and this should be the, in a way, our priority should be continuous logs, and then maybe secondly we can use DST data that I mentioned, DTS data that, as I mentioned before, and as a third step, as a third priority, we can recommend that the BHTs and the DSTs can be used for the geothermal gradient measurements, and we highly recommend to correct the BHT temperature before calculating geothermal gradient. And this is what I can explain and talking about today. If you have any questions, please do not hesitate to ask me.